Good evening to you all, and welcome to the April Smart Grid Educational Series seminar coming to you live from Foster City, California at the IBM Innovation Center. We are going to be talking about some novel schemes of financing the next wave of investments in smart grid. I'm going to be talking a little bit about the technology and some of the issues first to bring everyone on a level playing field, because quite often we have people with different backgrounds, and it's important to share some information about the smart grid and what are some of the technology and business process issues before we can create the value proposition for investing in the next wave of smart grid R&D. So our agenda includes talking a little bit about what smart grid is quickly, and then talking about what it takes to put one together, some of the environmental drivers that involve like carbon and other things, and then some economic drivers for smart grid. Why does it make sense to have smart grid now, given the current economic situation in the world? And then some technology drivers which are accelerating the development and deployment of smart grid. Some labor drivers that talk about some of the issues with the workforce and where the workforce is headed, and how does that impact the electric sector. Then I'll get into the value proposition for increasing smart grid R&D investments. Where are the gaps? Why is it necessary to fill those gaps? And what would it take money-wise to do that? And then some possible options for financing from the private sector. Now notice, when I say private sector, let me be very clear that I'm not talking about looking for money from the federal government in outright grants. I'm also not looking for money from the public utility commissions to put as surcharges on the bills of customers, because that to me is just another form of a tax. I'm talking about what options can we create to take some of the wealth of this country, the $2 trillion that are sitting in the reserves of many, many companies. What incentives can we create for them to unleash that money in proper financing schemes that can then fund research and development? We've seen that in electronics. We've seen that in healthcare, starting out with some stimulus from the government, but moving into the private sector where the proper value proposition was made for private sector to put some of their bottom line money, the profitability of their companies, into long-term R&D programs. I feel, and this is where my advocacy comes in this presentation, that nothing short of that is going to help us meet the challenges of the future in smart grid. That this is not going to be just something that DOE or DHS or NIST or NERC can throw $2 million, $5 million, or $10 million and solve. And the more that we head in the direction of distributed energy resources and renewable energy, the more I feel that relying on the private sector to address the R&D issues is going to be important. And then we're going to open it up, not just for Q&A for this presentation, but this is the time when you will make your contributions, the people who are sitting online and the people here in the room who can critique what I am presenting, but then also provide your input of creative schemes you may have thought of that would allow private sector money to come out. First of all, we know that there is an electric grid. It's been around for over 100 years. So what is smart now that wasn't there before? My argument is that the electric grid has become gradually more and more intelligent, but hasn't been smart until of late. A lot of people say, well, that's the same thing, and I disagree. It's intelligent in that individual systems that are on the transmission and distribution domain have the ability to retain more and more information, more and more granular information. So they're becoming more intelligent. So whether it is ABB or Areva or Siemens or any other manufacturer, the products that they're putting into their T&D systems as a result of the evolution of electronics have become more and more intelligent. But the reason why we wouldn't call this grid smart until of late is that we haven't had adequate networking between those intelligent systems to move the information from where it was created to where a decision needs to be made. That used to be limited to a network operations center and maybe some high-value substations over a wide area network. And that wide area network had a variety of communication technologies that would connect it, like twisted pair, maybe some fiber, some wireless type, microwave type technologies. But then when you get past the substation, it was few and far between. In highly urban areas, like in cities, you would see more networking because the distances were short. But in utilities that had large service territories, it became very, very cost prohibitive with the old technology of comms. But now that communication technology is becoming more readily available and more cost effective, and the sensor technology is getting better in miniaturizing, we have the ability to gather information and network it better farther and farther out on the grid. So that's a big paradigm shift, and that's why I now call the grid smarter, because it knows, like smart people, how to use information. Intelligent people hold lots of information. Smart people know how to use it. And so the grid is going from intelligent to being smart. Because I don't like it when people keep saying, well, we have an antiquated grid, and if Thomas Edison came, he would think it was just like the one. No. I disagree, because they've never been to a substation. They don't realize how much information a utility service operator can extract with his industrial-grade laptop when he goes to a substation. Then that has been the case for many, many years. So it's not the case that it's an antiquated grid from that perspective. But to deal with the new challenges with distributed energy resources, with demand response, and all the other applications, we need a highly networked grid. And this is why we call it a smart grid. So one key part is to increase the IQ of the smart grid, you need to have back-end integration. All the various application servers that sit in the IT and the OT side need to have adequate networking amongst them and the ability to exchange information. The semantic model has to be consistent across those servers so that information can be readily exchanged without requiring a one-to-one kind of correspondence and mapping of objects that is manually very intensive. And that has been a major hurdle for many, many utilities. Ironically, co-ops and munis, as a result of having a particular protocol, were able to integrate their servers on the back end much, much more effectively than many of the larger utilities who are still discussing what model to use. And now there is major effort in NIST, in the domain expert working groups, and also in the domain experts from Society of Automotive Engineering, for instance, the ZigBee Alliance, the T&D Duke in particular in NIST. Objects are being developed to represent those attributes in transmission distribution systems. So when they are brought back, they can be put in this what's called a Common Information Model, or CIM. There's an IEC standard for it. For distribution, it's 61968. For transmission, it's 61970. And libraries are being developed to document all the granular attributes of the grid. And this is key in doing back-end integration, this CIM model. Just like it's very important to have a good object model for the field equipment to do the control, the SCADA side. So that's where DNP, the Distributed Network Protocol, and the IEC 61850 for substation automation are two protocols which are being used today in transmission and distribution systems to control using the SCADA with messaging. These things are critical for the IQ of the smart grid. So it's not enough just to say smart grid. You have to say, well, how smart is it? The more you standardize on the semantic model and make sure that those attributes are represented self-consistently in the model, and you have access to the information and you can make decisions in real time, the smarter your grid is going to be. So the back-end utility system integration is key. The two-way energy flow and communication is important, because how would we bring in distributed energy resources onto the grid, integrated at the customer level, at the distribution level, at the substation level, without having a two-way energy flow? You would not be able to do that. You have to control the network actively if you want to bring in distributed energy resources. It cannot be a passive network where you have centralized power just feeding a bunch of customers. Now customers are becoming prosumers. They are depositing energy onto the grid. So you have to actively control it to avoid it from becoming unstable, because renewable energy is unstable. When I say unstable, that means its supply varies. So the voltage can vary. And so you need to have the appropriate stabilizing mechanisms, either through storage or through shaping the load, to make sure that the voltage remains constant. That requires a lot of communication, a standardized object model to control the devices, and to make quick decisions. This smart grid has to be capable of supporting distributed generation. And why is this important? Because centralized power plants are kind of like going towards Jurassic Park. And the reason why they're going towards Jurassic Park is because of the cost of making them, the issue of congestion on transmission lines when you have a very high power output centralized plant and you don't have enough capacity on the transmission line, you can have an issue, and the environmental impact. So for that reason, environmental organizations and the policy wonks, combined with the consumers, are trying to push for distributed energy resources. Key part of that is distributed generation. So you can have solar farm, you can have wind farms, you can have storage banks, and everyone can play in this, small, medium, or large. That requires a lot of thinking and a lot of designing to make it happen. You want to integrate large amounts of renewable energy for very obvious reasons. Solar and wind doesn't come with a carbon footprint after the panels and things have been manufactured, unlike fossil fuel plants, which are constantly producing CO2 for every kilowatt hour they produce. But renewable energy, there is a carbon footprint in the manufacturing of the equipment, but when it's installed, except for the fuel that the truck uses to maintain them, the carbon footprint is low. Higher levels of substation automation. Why do we need that with smart grid? Because naturally, when you're going to integrate solar and wind and other renewable sources, you have to have an intelligent substation. You cannot just rely on the NOC for everything. And this distributed intelligence will allow for higher availability, greater reliability of the grid. You can even create more resiliency by having substations talking to each other. This requires a certain level of automation in the substation. That's why these protocols for substation automation are so important now, that every granular attribute of every device is represented in the SCADA system. And then you also need high-speed networks to be able to communicate, to deal with things that are very time-sensitive, sometimes to the order of 4 milliseconds for certain protective relays, for instance. You want to reduce the line losses in T&D systems. We have just accepted for years that we'll lose 7% of our electricity on T&D. Now just do the math. If we have 1,000 gigawatt output at peak in the United States, that would be like 70 gigawatts of loss. That is more than all of South Korea's electricity output. So all the Kias and the Hyundais and everything, Samsungs that you get, come from the electricity we're losing in the U.S. on our grid. Now, if ohmic losses, the loss due to resistance on a wire is only 1 and 1.25%, what's the other 5 3/4? It's all inefficiencies in the system. Because of lack of awareness of what's happening on the grid, we overcompensate, trying to make the voltage acceptable at the other end. If we had better sensors, if we had the information from the smart meters fed back into our SCADA systems, we could plan better. And we could control the voltage better at the edge. And therefore, we could reduce the losses. If we had sensors along the line, we could see where the faults are, and we would not waste electricity. We would just stop flowing electricity in those segments until the fault is cleared. So these types of technologies, I'm now talking about the bowels of T&D, is where a lot of the IQ of smart grid is needed. And yet, you hear so many people equate smart grid with smart meters. Notice how little I've spoken about smart meters up to now. And I have spent 4 years at EPRI doing research on smart meters. So I know how important they are, but they're not the end all. And it's important in our dialogue to keep the importance of T&D in smart grid alive, because that's where a lot of the research is needed and where a lot of money is needed to make it happen for the next generation of smart grid. Now I'm getting into the customer prem. Why is it important to integrate the customer prem in smart grid? Because if we want to engage the customer in a meaningful exchange with the utility and aggregator, we have to integrate the customer prem and not consider customers as a load going forward, but really as a partner. Because if we are going to depend a lot on renewable energy that is available sometimes and not at other times, and it becomes a large fraction of our energy mix, we have to have a positive engagement with customers to modify their behavior in real time so that the demand for electricity somewhat follows the supply of electricity that we can have. We don't have the luxury of large reserve margins the way we used to with centralized plants. So we have to think about that. Integrating the customer prem means being able to send a signal, a demand response type signal, or a load price control kind of signal for peak price, or load curtailment signal. And what it can do is, whether it goes through the meter or it comes over the internet through a router, it can go to a variety of appliances, and it can turn off or change the mode of behavior in real time in order to reduce the energy consumption or maybe bring it back when there is ample supply. So this is why it's so important to integrate the customer prem onto the grid. So now we're dealing with customers as our partners and not as a liability. Applications like demand response, electric vehicles, and AMI, all of this is meant to help make the overall grid more energy efficient, because if we can use demand response very effectively, and we can level or bring as close to level as possible the demand for electricity during the whole day, we are going to rely on as much bulk power sources as possible to energize the economy. And the nice thing about the coal and the nuclear and the hydro is that it comes at a very low wholesale price for electricity. And so if we have a very high utilization factor of that plant, rather than just heating up the atmosphere, it's really turning it into electricity, which is fueling the homes, we will rely less and less on peaker units that may be running on natural gas or other things that may only have low utilization factors because they're running only during those hours when there's a peak. So the marginal cost of electricity is very high from such plants, because you build the plant and you pay the money, but you're only using it maybe 2, 3, or 4 hours a day. So the more you level, the more efficient the use is, and the lower will be the cost of electricity for the customer. So AMI and DR kind of go hand in hand. And the reason why AMI is so important is because we are in the utility industry that's highly regulated. We can't just assume everyone has internet connection. And this is why smart meters were such an important part of connecting customer prem with the grid. Even though 91% of homes in the United States are cable ready, it doesn't mean they have cable service. They're just cable ready. So to assume that they have internet, broadband, and all, now, of course, the number is increasing with each year as people are relying on it for more and more of their daily lives, but we can't assume it as a regulated industry. So that's why the public utility commissions of various states have advocated smart meters as a way to get into the customer prayer, because everyone has electricity in those homes, and therefore the meter becomes the gateway. EV is an additional, it's like a bonus. Electric vehicles are the connection between the utility industry and the transportation sector. So because the transportation sector has the largest carbon footprint of any vertical in our economy, it makes sense that if we're building this infrastructure to make the grid smart, that we also enable electric vehicles to reduce some of the burden of the transportation industry in the production of carbon. So EV charging and the amount, it's almost like 1 to 2 houses when you charge on the high end, because the wattage is about from 2.5 kilowatts to 7.5 kilowatts. And a typical home is about 2.5 kilowatts. So it's like 2 homes at the high end, or as many as 3 homes at the high end. So imagine if you had a Tesla. You know, God gave you lots of money and you bought one, all right? It's possible. Or you won the lottery, I don't know. Or you inherited some money. Whatever happens, and you got this Tesla, what do you think your neighbor is going to do? They're going to look at you, and they're going to start having domestic issues. They're going to tell their spouse, I want that Tesla. Well, what about that vacation you were promising me? I want that Tesla. Look, it's only $10,000 down payment, no big deal. And they'll get it. And pretty soon, the neighbor next to them will, and that poor transformer on the street is going to not like that. Because when they come home at 6 o'clock and they connect it, all of a sudden you've got a big problem on your hands. So this is a real serious issue, and that's why EV, AMI, demand response, they kind of all go together. Because if you want to have sustainable growth in economy and deep penetration of electric vehicles, and EPRI is doing a lot of good work in that area in their electric vehicle program, where they're looking at the impact on the distribution network with different forecasts of penetration of electric vehicles on the grid. And this is a serious issue, because the proper planning by the distribution companies to put out the transformers, upgrade them at the right time, you almost have to connect it with DMV. That when someone goes and registers an electric vehicle at DMV, the DMV sends a signal to PG&E or any other utility and say, in your area, in this address, there will be an electric vehicle, so that they can start planning better. Nothing short of that is going to work because of the impact, immediate impact it will have. And then empowering customers for managing energy usage. Informed customers are better customers. They're more reliable, they're more responsible, there's a sense of accountability. So the Prius effect does work. And there have been studies, I believe one was at Salt River Project, which is the utility out in Arizona, that had meters set up for prepay. And part of it was a display that showed how much energy they use. And the people who subscribed to that were using 12.5% less electricity than the average population, just because they knew how much they were using and they paid in advance. So it does have an effect. So if you want them to be your partner, you got to share information with them. And the closer to real time you can make it, the better. I'm not suggesting real time, but somewhere in the hour or so afterwards, they should be able to go on a smartphone or an in-home display or on a website and see what they're doing. Now, I said something, but it has huge implication from a data management perspective for a utility. because they have to literally pick a needle out of a haystack. There's so much information coming back from a smart meter. Data is just a very small part of it. It's all the logs and everything for voltage, current, phase. It's NCC 1219 tables. There are many of them. One little part of it is energy usage. So they have to parse all of that data, make it available on a demilitarized zone in the enterprise, and publish it for customers to come in and pick it. It's not that simple. But utilities like PG&E and SCE and others are doing a great job of making all of that as automated as possible. This is a very heavy slide, but I wanted to spend the time on this to show you how critical smart grid has become for the prosperity of our nation and for how many things about our day-to-day lifestyle are going to be connected to this. This is just leisure now. You can relax with this diagram. It's like Visine to your eyes. And it just shows you the 7 key domains as defined in the NIST first phase interoperability project. You've seen this slide multiple times. If you haven't, just do a search online for smart grid with images, and this will be like one of the first ones that'll come up. But the key thing to understand is that the lower layers, the 4 domains, are the ones that are connected electrically, and the 3 domains on top are connected via communication links. But this was a very easy way to bunch the problem up into these domains. Going further, the question is, how do we create a smart grid? Well, there's an EPRI IntelliGrid methodology which has actually turned into an IEC standard. And this is the exercise, basically, of how you create a smart grid. This is the nerdy, geeky, detailed version. This is where you can yawn and it's okay. The first thing about developing a smart grid is collecting narratives from domain experts who use it. You have to ask them, what do they do on a day-to-day business? Their narrative are the use cases. They're words. But someone who is technical can listen to those words and distill from it the architecturally significant parts. When I say architecturally significant, I mean things that are relevant to the physical and MAC layer, the network layer, the transport layer, the application layer, the semantic layer, the business layer, and then eventually the policy layer. All of these are defined in what's called the Gridwise Architecture Council stack. There's an interoperability framework white paper. I would recommend that you get it. It's a must-read because it will organize in your mind visually the logical layers on which all of this smart grid rests. And Marty, notice I didn't even write his last name. And the reason is because it's Marty's template. It's Marty Burns from Hypertech who made an amazing contribution in organizing the use cases, and literally, just like you have a juicer machine where you throw carrots and stuff, you can literally drop the use case into Marty's template, and sure enough, it'll filter out and give you by layers what the requirements are in each layer, if it's relevant to that use case. So we do the use case analysis. We distill from it requirements. The requirements are on communications. The requirements are on cybersecurity. The requirements are on objects, attributes. Those requirements then are seen relative to the standards that are relevant in those domains where the use case is being applied. And you go down to the granular level of the specification in the standard and say, does this specification meet this requirement, yes or no? And if it does, great, that means it's supported. And if it's no, that's a gap. Then the standard specification groups, a lot of them are sitting in the various domain expert working groups of NIST, are now fleshing those specifications in the standards, so that the next version of the standard will have those specifications to meet those requirements. Then after that is done, you now have a set of new specifications. You furnish those to the product vendors, the TIs of the world, the ST Micros, the iControl 4, whatever company. in whatever domain, Eaton's, Siemens, everyone, and say in your area, the product that you're making, in this domain, you say you're adhering to XYZ standard. You have a gap in that standard, which does not allow you to meet certain requirements of these new use cases we've just analyzed. So go and create your new version of your product that will be consistent. And by the way, once you produce the product, we will test it in labs that we approve. I mean, I'm talking as an industry, to make sure that they're compliant. Because until that compliance is not verified, interoperability is not guaranteed. Because if multiple vendors have multiple understandings of the same standard, and there's no testing and certification, you've got a problem in your hands. Then you will not have interoperability, and you are going to put your technology at financial risk. And then, after you've got these products and they're working and everything, it's still not enough. Now you need to educate a workforce to be able to say what I just said. And not only that, but actually program and test and verify, and then be part of utilities and aggregators and vendors to support all of this. And that's my last bullet in this slide. That education part is critical. Notice that each one of these things is important for making smart grid happen. Unfortunately, a large part of this has been happening on a voluntary basis. And I say unfortunately because it's not sustainable. People have to pay for bills. They have to live. And it's very difficult for someone to have a full-time job and then on a voluntary basis do this. This is a full-time job. So we have been using very small amounts of federal money to feed a very small group of people who are full-time on this, while a vast majority of people are working as volunteers. This has to change if we're going to accelerate this process and have accountability and transparency in the process. And I say this because 4 years ago, when I organized the first workshops for NIST for the interoperability framework, I said this is what we need to do. But I was hoping that the private sector will get into this in a big way and fund this, but they haven't. A lot of them have relied on the federal money or whatever was guaranteed from the CPUC or other PUCs, and that's the only money that we seem to see around. And the purpose of this presentation is to show you the enormity of the exercise, to put the fear of God in me and you, that short of this kind of massive R&D investment, this kind of complex exercise cannot occur to fruition, to full fruition. We're seeing little bits of it, some progress. We've got smart meters deployed. We may have some DR services, but it's still a very small part of what is possible with smart grid. This is just a diagram to show you within the environment that when we analyze the use cases, we realize that these environments within the domains need to talk to each other in this way. This is just to show you the different levels of complexity. So you saw the little cartoon diagram. This is a little more detail showing what systems need to speak to each other. And I won't go into the detail. I just want you to capture the complexity of this. But realize that there are very good domain experts who are on the verge of retiring who gave us this information. And this is how we have this in a nice diagram like this. Moving along, the use cases will create a bunch of little systems that need to talk to each other. And the NIST working groups did an amazing job of documenting all those interfaces. And these are not uranium isotopes that you're seeing here. These are the interface index numbers on what's called the spaghetti diagram. These are all the ones that are relevant to advanced metering infrastructure. So when you are a vendor and you want to build product, you got to know that you have these interfaces and what the requirements will be for you to exchange information with other systems, because you cannot guarantee that one vendor will own all of it. And this is why the whole standards development process and interoperability is critical. Moving along, here we have the full enchilada. Well, I'm mixing metaphors here because it's the spaghetti diagram, but I'm calling it the full enchilada. So excuse my two cultures coming together. But all the use cases together looks like this. But when you look at this, the main thing is that everything has been documented. And so vendors who operate in little narrow slivers of this know exactly who to talk to. And that's the important thing. See how much work was involved? This is like the Human Genome Project for smart grid. These are little peptide links now. All right, moving along. Trying to wake you guys up. Let's talk about some of the environmental drivers. We know that the Kyoto Protocol, while a lot of people are not following it, but it's a guideline. And it's basically saying that in the next 40 years, we've got to reduce our carbon footprint by 83% relative to 2005 levels. And naturally, utilities have to do their fair share. Centralized power plants have certain issues. And that is why consumers are kind of losing interest in them. One of them is, of course, the greenhouse gases for coal and for nuclear as a result of what happened in Fukushima, or what didn't happen but people thought happened. The result is that people have just withdrawn and said, I'll just have my solar farm. I don't care about the bats. Let them die in the wind farms. At least it's not going to be me. I don't know. They have come up with some argument, and they think that the panacea or the savior is renewable energy. And drill, baby, drill. Build as much natural gas as you want because we've got supply for the next 100 years. Why do we care? Well, we care. We care because we are concerned about the sustainability of this planet. Carbon is just one dimension of it. But the public is where it is. And we need to deal with that. And the public is saying, no more centralized plants. Just go to any hearing where a utility is trying to build a new power plant and see how contentious the environment is. It's really bad. But this is the reality. Also, the issue is when you make the power plant, you take a lot of precious resources to build it. Now, it's great from a job creation perspective, but from a natural resource perspective, it's cumbersome. And the nuclear power, and I'm a nuclear engineer myself, and I love nuclear energy, but the way it's being done in this country today takes 7, 10 years, billions of dollars. Many utilities are not able to afford, their balance sheet cannot underwrite the production of a nuclear power plant because it's too expensive. So these are issues with centralized plants. And then, of course, marine life. There is significant change in temperature that occurs in rivers when you have the outflow from a power plant. And that is also an issue because a lot of communities depend on that marine life, whether it's fishing or whether it's the ecological balance. So we have to be cognizant of that. This is the diagram. Again, Visine for your eyes. You see the slide coming down over 40 years. And this is something that EPRI put together from their PRISM study a few years ago. And I will show you another diagram. And this is where it's called the PRISM because it shows all the savings in carbon by enabling all of these technologies. Starting with energy efficiency, the connection is direct. Less electricity you use, the less pollution there will be. Renewable energy, again, solar and wind with low carbon footprint will help. Nuclear, because it doesn't have a carbon footprint in the production. Yes, there is a carbon footprint in the mining of the uranium and transporting it. There is a carbon footprint in the production of the nuclear power plant. But the gigawatts that it produces, there's no carbon dioxide being produced from that reaction. So that's why there's a significant saving in carbon. And France, as an example, in a future with carbon trading, carbon credits, will do wonders in selling those carbon credits because of its nuclear technology. Fossil efficiency is about, getting more joules of mechanical energy out from a certain pound of coal or a certain amount of natural gas, so that helps. Carbon capture and sequestration, CCS, is about just taking the carbon out of a coal plant or a natural gas plant and not letting it be released in the atmosphere. That helps. Electric vehicles definitely help because now you can have cleaner sources of electricity running those cars. Electrotechnology, so instead of using chemicals and fuel, you use electro technologies. And EPRI, again, has done very good work in showing how the improvement in efficiency occurs by using certain electro technologies. Because if, like, you want to heat something, you just bring the heating rod to where it's needed rather than heating up a whole room, that kind of stuff. What are some of the economic drivers? Well, one big economic driver was the $4.3 billion that Department of Energy awarded to 99 recipients, who were utilities mostly, and there were some other organizations. That put some money in the economy, and the value propositions of smart grid were there, so people started investing. There was a public-private partnership in many cases. The DOE asked for cost share, so that forced private sector also to put up some money. And that generated some prosperity in our sector for the last 3-4 years. Another economic driver is this technological revolution in cybersecurity, in communications, and also in these ARM processors. The ability with very, very small form factors to be able to do stuff. I mean, I'm just amazed. I've seen some vendors who put cybersecurity controls on things that are just literally, I can't even hold them in my hand properly. And it's a full computer in this little form factor. So by bringing that kind of capability, that created an economic impetus for smart grid, because now things are possible with handheld devices that were not possible even 5 years or 10 years ago. Of course, solar and wind, there's a renewable portfolio standards requirement that's driving a lot of this. So wind and solar technology is getting subsidies, and that is what's driving a lot of this. And Germany is a good example of that. But in the US also, they're getting, especially California, they're getting a lot of incentives. Moving along, storage technology is becoming less expensive. Now, I have to warn you that storage will not follow Moore's law. Storage follows Mendeleev's periodic table. Sorry. So why is that important? Because the valency of electrons, the energy that is required to excite them in an atom, doesn't care about Silicon Valley. It's what it is. And certain combinations of elements will hold a certain amount of energy in their chemical compounds. And that is what the storage will give you. I'm talking about chemically based electric storage. There may be other types of storage. There's thermal storage. There's other storage. But I'm talking about the stuff that we are depending on largely for this business. So don't expect major miracles happening in this type of thing. You can play games with economies of scale, in automating the fabrication and all of that, but it's not going to be just magically some element is going to come out of the periodic table. Believe me, people have been checking it out. And the problem is that some of the higher yield ones also could be more flammable. There are other issues. So you've got to keep a holistic view. Don't just be a one idea person. Look at it in a holistic manner. But it's becoming cheaper because the manufacturing process is becoming more efficient. And other technologies that don't have to do with the chemistry of the battery are getting better. So overall, it's becoming less expensive. And then, of course, the growth in the electric vehicle market is definitely driving smart grid now, especially with the Teslas. I don't know where the money is coming from, but everywhere I look, there's maybe it's the same one that's just going around me. But there seem to be a lot of them all of a sudden.
They have released about 12,000 in just last.
12,000. Wow. Okay. What are some of the technology drivers? Well, smart meter was a big driver for smart grid because naturally, when you have all these applications that are enabled by smart meters, then you would want them. So it's like a precursor. Smart appliances. All types of, whether it's refrigerators or whether it's pool pumps, water heaters, programmable communicating thermostats, they're putting smarts in them. And whether it's a proprietary protocol or open standards-based protocol, it doesn't matter. They're coming out in the market. Even Lowe's is carrying devices that are smart. Distribution automation technology. I talked about this earlier with sensors, with things like smart switches, relays, those kinds of things that are getting the smarts on them that can make decisions by sending a signal to them. This is helping distribution automation and reduce losses. So this is a key technological driver in smart grid today. Phasor measurement units. We saw after the collapse of the grid in 2003 with what happened in Ohio, we learned that a better understanding of the condition of the grid, the voltage, current, and phase at different locations in real time and coming very, very fast back at you, can give you a very good picture of your grid. So if the condition is worsening in a particular area, you can take corrective action to limit its influence and not let it bother everything. Phasor measurement units, suddenly their value went up, even though they're very expensive. But people are making the arguments, and the public utility commissions are approving these at about the rate that the fire department approves fireproof jackets. I mean, it's amazing. It's one of the easiest hearings to go to, is a PMU hearing. My theory is the lower the voltage, the more the arguments. The higher the voltage, the less the argument, because no one wants to touch the electric third rail, right? Okay. High-speed communications for Han, Nan, and Wan. I mean, that doesn't sound like English almost. But this area has seen a lot of growth with mesh technology and broadband, with Wi-Fi, and by putting the smart energy profile on top of these protocols and enabling the home area network, it's suddenly giving rise to deployments in California, Ohio, Texas, and other places. In NAN is where the AMI's fabric sits, the mesh network. That saw amazing progress because of the 802.15.4 protocol and the mesh, and Silver Spring and Itron and Landis and Gear, all of them jumped on the bandwagon with that. And then the WAN technology has improved significantly with LTE type technology, WiMAX, and others. And of course, there's always fiber. Cybersecurity technologies with small form factors. This is what I was talking about, that ARM processor, and being able to, on a very small board, have the smarts of a computer to bring the latest cybersecurity and communication technologies to even legacy systems. You just literally hook them up. There's a company called Gumsticks that literally does that. You can plug it into the legacy device and you terminate all your services there, but the legacy system is, think of it from a NERC SIP compliance. It's amazing what you can do by bringing these controls right to the front door of an old system. That was not possible before when the form factors were big. Today, it'll sit on a nice little chip. Big data management, again, a big technology driver. All this data coming, parsing it, storing it, reporting it, and the fast computing capability that allows us, and the switching mechanisms that allow you to take lots of data and switch it fast. This is all in the last 10 years, and now we're seeing the fruits of that. Standards for interoperability. I mentioned this earlier. If you don't have that semantic model, if you don't have proper standardized messaging across vendor products, you're in deep trouble, because your SCADA system will only operate with your vendor product and not someone else. So having these standards of interoperability is a key enabler for smart grid from a technology perspective, and then, of course, handheld devices. Moving along, this is a nice little pictorial that shows you the layers in smart grid from another perspective. So I showed you holistic domains, but it was a flat diagram. This is a layer diagram. So if you go to Max's Diner and ask for the 7-layer cookie, that dessert, these are the layers. Pick your favorite. The reason why I show this is there's a lot of expertise that goes at different types of expertise in creating this smart grid environment. You could be a database analyst. You could be an application developer. You could be a comms expert. You could be a power engineer. See all the skills that are involved here in the different layers. But this was a very, very good contribution. EPRI initiated this concept, and there were other parties that are involved in creating this. But I really like this slide because it kind of shows you smart grid in a nutshell without simplifying it too much. It's showing the complexity, but in an elegant way. some applications. We talked about phaser measurement units to control transmission. We need things to do substation automation, like condition monitoring. We've got distribution automation to do control voltage reduction, as an example, volt-var optimization on the distribution to make the distribution system steady so it doesn't do this. Because if it does this in voltage, a lot of end systems will shut off. They don't like a lot of variation in voltage. US, by the way, has a tighter control than Europe does. And that's why Europe has been able to accept more renewable energy than the US has because of this tolerance. We have very tight tolerances. We have opposite relationships with Europe. When it comes to building cars, we have wide tolerances. That's why our vehicles, when you shut the door, it sounds like it didn't shut, so then you try to shut it again. European cars, you know, when you shut it, feels like a cockpit almost, right? But when it comes to voltage variation, we seem to have just the opposite. We are very tight on that, and Europe is a little more lax in their industrial controls. But this is very important in DA, is the voltage variation. You don't want that. And then, of course, you've got customer prem. All right. This is the back end. I mentioned to integrate, you need to have some kind of a bus. And this is an application layer highway that connects various servers and allows. So the underlying communication doesn't matter. It could be whatever it is. But this is a higher layer concept of having addresses and like a network at the application layer that integrates and allows you to exchange information. This is a slide I borrowed from Albedo, and I think it's a good slide because what it's showing is one of the challenges that smart grid is facing today, that traditionally the IT and the OT side were two separate environments. They almost did not talk to each other. And I say almost because in some utilities they did, but in many they did not. And when deregulation happened, it was even worse. So what is now needed in order to enable smart grid applications is that you have a touch point in IT and OT. So while it does create a cybersecurity risk because the enterprise through a firewall is then connected to the public internet in many cases, you still need information from the IT side to do OT stuff, and you need OT type information to make IT type decisions. So the proper firewalling, intrusion detection, antivirus, and all of those mechanisms need to be there in addition to having situational awareness and having plans for mitigations in case there is a violation. So security teams and utilities are sitting and developing these processes, failure scenarios. And each failure scenario then has a mitigation. But it's important to understand that these two should be properly firewalled, but they are needed together to make it work. The distribution automation is complex. It has many, many parts. GIS to tell you location, asset management, down to the screws and the firmware and everything, keeping tabs on it. Outage management system. Look at how many applications are in this environment. And many utilities spend millions of dollars internally and to organizations like EPRI to do R&D in this space. This is a big part of the EPRI practice in power delivery and utilization, is working in this space in a collaborative way with multiple utilities. This is very, very important. IBM does a lot of work in this space in terms of integrating all these information systems. Each one of these is sitting on servers, essentially. They're not floating in the air. They're sitting in data centers and network operation centers, and it's very important to have the right information at the right time so that the planning model, which is the main thing here, is moved from a probabilistic model to an empirically based model. Because the empirically based model will not only converge faster, but it will be more realistic of what's happening out there, and therefore will be more stabilizing. This is a diagram that shows, again, from the NIST work, but the three basic environments within the larger home area network, industrial and commercial space within residential sector. And there are multiple applications in each. Now, there will be different protocols running in each of these sectors. Industrial is a lot Modbus. You'll have a lot of BACnet in commercial buildings for HVAC. You will have LawnWorks a lot of lawn works in there with street lighting and things like that. And then home area network, you'll have ZigBee and you'll have home plug. There's a lot of Z-Wave that's there in the install base, but that's mostly for home automation, less for energy management today. And of course, Insteon is there. That precursor was X10 and webcams and things like that. So there are multiple protocols in this space, but we are moving towards standardization of one or two in each area with great interoperability through application layer gateways that we are building. All right. Again, a diagram that's showing in a home what the future home could look like. And think of all of these devices that could be potentially controlled for very granular demand response programs that could turn on and off or change the mode of operation of devices. And as a result, we're able to level the consumption of electricity during peak times. Now let's look at some of the labor drivers. Enough on technology. Let's go to the humanities and art side of the business. So on the labor side, look at the average age of the workforce in the electric sector. It's over 47 years. Now, most people live to their mid to late 70s. So 47 is middle age, not a big deal. Not so. There are a lot of early retirements occurring at 50, 51, 52. They're not going all the way to 60 or 65. So when the average workforce is 47, imagine how many people are sitting teetering on retirement. And sure enough, by 2020, 62% of the current workforce will be gone. That is substantial because the Gen Y that's coming with the earrings, the tattoos, the piercings, and all other paraphernalia are a different breed. And we better be ready for them because our reliability of electricity will depend on whether they're twittering at that moment or tweeting or whatever they call it, or they're Facebooking at that moment. So we need to create an environment that's conducive for their culture. This is a big shift. I mean, we tend to make fun of it, but they're going to produce, or they're going to help us get the electricity. So we need to think about handheld devices and try to put as much of our day-to-day work in the utility industry in their hands so that they can live their lifestyle, but they can also solve the problem. Because if they are not motivated and they are slack off, we're going to have a serious problem. And you will see something about the older workforce that's retiring. If you speak with them, and it's important to go and speak to utility people that are older. They don't just do a job. They really feel like it's their calling. And they're very, very sincere people. They may not get paid that much either, but they're very dedicated to what they do. Now imagine replacing that with someone whose first thing in their mind is, how much money am I going to make? Am I going to get that fancy car? It's a value change. So what I'm saying to all of you is that maybe technology can help bridge some of that gap that's going to be created because of the cultural shift. We need to capture the domain expertise of the people who are retiring by creating the proper information systems and knowledge-based systems so that we can preserve that learning. And we need to find friendly ways of communicating it to the new generation so they remain motivated and can give us the 5 nines of reliability that we're used to. Automation is only going to help so much. Human beings are always an active partner in the delivery of electricity. So then the new workforce will demand higher wages. There is currently a $20,000 a year differential in what EE majors make who are in power systems versus other areas of EE. And this gap has to go because the expertise that's required of them with comms, with cybersecurity and everything is just going to be like any other discipline of EE. So why should they be paid less? So that gap has to be filled. Just like we are addressing the issue of the 69 cents to a man's dollar with men and women, we need to address this issue. These are critical issues. We tend to get so focused on technology sometimes, we forget the Achilles heels in smart grid. Motivated workforce is key. All right. Now I'll get off my soapbox.
Chance.
All right. For the people online, someone in the audience said fat chance. And I accept that. Okay. Now, let's think about what can we do to increase R&D spending in smart grid. Well, one argument is that this voluntary effort is just not going to continue to work. They're already feeling the pressure. And I have seen that in the aging process of the volunteers in the interoperability thing. Every conference I go to, they look a little older than they did before. And the aging rate is faster than the months that they have lived. And the reason is lack of sleep, lack of proper nutrition, traveling a lot, because they're doing a job and then they're doing this on top. Now, they're doing this for their intellectual interest, and their bosses have said, yeah, you need to be a part of this. But they're not getting compensated. It's not like they're getting a big bonus from their primary employer. This is not a sustainable model. So my argument is that we need to increase the funding just to bring more volunteers into paid work so that they don't have to do a full-time job and then do this on top of it. And then they can spend more time and we can demand more from them, because when it's volunteer and they deliver something late, what are we going to do? They're volunteering. So you don't have as much control over the process. The second thing is that all this technology that's coming out of academia and national labs is not ready for prime time. It needs a period in between where its pilots are done, small-scale demonstrations are done. That requires people, that requires time, and that requires money. If we don't do this, what will happen is individual vendors will grab a hold of that technology. They may buy it, and they may shelf it. And then we will not have the pleasure of using it. This can happen just to avoid the product coming into the market. But if we had some way of funding this middle stage, what I call, and EPRI, by the way, can play a big role in this, because when EPRI shows its marketing diagrams, it shows itself as the circle in between academia and universities and commercialization, that we are the ones in the middle. But with utilities reducing the amount of money in collaborative research because they have to look at their bottom line, this minimalist game cannot continue endlessly. So there'll be less and less money for that type of collaborative research, and the result will be that these amazing technologies that are coming out of universities and national labs will not see daylight. And then the intermittent aspect of solar and wind, I cannot emphasize it enough. I have created parallels of what this is like. It's like you're spending a nice leisurely afternoon in the pool with the sun out, and some naughty child is just jumping into the pool, splashing, and the water is waving in every direction. And you're like, would you stop jumping into the pool? That is solar and wind. What it does to a grid is what that naughty child does to a pool. Voltage, think of voltage like water going up and down, the waves. So you need things to stabilize the waves. That requires research. It requires research in informatics to do real-time balancing of supply and demand. It requires research in the batteries to allow some of the cushioning. And it also requires doing studies on human behavior to see the impact of DR programs to see how effective it will be. All of this is important, but that requires money. So I'm building the case for areas that we haven't even started to think about. No U-turns allowed with renewable energy in 20 years. We have the window of opportunity now. But in 20 years, with the way we're going with renewable energy, if we decide it's not a through street, we are going to spend the next 10, 15 years with 8 to 10 hours of no electricity while we figure out a workaround. So if you want renewable energy to be the only game in town, then be ready to walk that. because in 20 years you will not have that chance. So what I'm saying is where the investment is needed now is in alternative sources of energy. And in that, I will include fusion. I would include nuclear with small modular reactors, thorium fuel cycles, breeding and reprocessing, allowed again in this country. I would also look at flywheels. I would look at other sources of energy on this planet, not just solar and wind. I'm not saying anything against solar and wind. All I'm saying is don't make it the savior of this planet, because it's fickle. When a cloud comes over, it doesn't care whether you're producing electricity from the sun or not. It will cover you. And then you have a problem. And while molten salt and all those ways are nice, but they're at a huge capital expense. So keep all of that in mind. And of course, skimming the reserve margin. When you move away from centralized plants, you are removing that luxury of having that reserve spend. You're now using communication and control theory, basically playing this game like a tightrope walk in a circus, and you're reducing your reserve margin. You could have it when you had coal plants and nuclear plants and hydro plants. Now, if the reserve margin is getting skinnier and skinnier, and we're moving to DER, we better do some real good research on what impacts it's going to have on overall reliability, what it will take to build more resiliency into the system, how will we make it more secure, because now we have all these new threat vectors with all these partners participating in producing this electricity and consuming it, and safety. When I say safety, I'm talking fires. I'm talking about cascading failures and those kinds of things. So we need to research these, develop more elaborate scenarios, and come up with proper mitigations. We can't just tell a guy in a circus the first day, hey, here's a long rod, just climb on that rope and walk. And you know, the rod will balance you. Well, you know how many times they fall into a net before they can walk that tightrope? We need to practice. That requires money. And I don't need to say any more about electric vehicles. I made the case that its impact on the grid is going to be so huge once it starts getting into the teens and 20% kind of penetration, that we need to really think about the next generation of transformers. And I'm talking solid state, you know, where we can use electronics. Why are we using these transformers from 100 years ago, that design, today, given the fast response that we need? The ironic thing is that the wire can handle it, but the transformer can't. Isn't that amazing? That it's supposed to be the other way around, right? The technology should be ahead of the wire. No, the wire is futuristic, but the transformer is old. So we need to bring in more of the electronics knowledge into transformers to change that. Now, this is where I wanted to bring you. It was very important for me to set the stage, because you got to have an appetite before you're served food. And I wanted to give you the appetite, because now I'm thinking of some ways in which we could possibly raise funds and not just go for institutional money. I'm not about going down to Sand Hill Road or Hamilton and saying, okay, just give us $3 million or $5 million. Create financial instruments that allow small people, individuals, to participate also. Now, there are some very creative schemes, like I've heard one with solar panels, where you can buy for $25 a share in this company that provides solar panels. And as they sell electricity from putting that panel up, everyone who made that investment gets income every month. So they're like shareholders in that. And I've seen examples of companies that are owned by all the employees that do very well also, even in recession times, where everyone is opposed to, let's say, a dozen people owning majority of the share of a company, all the employees owning the shares. And you find much more motivation there. So one thing is what I call the smart grid mutual funds. And we could create them of different sizes. And maybe Wall Street could be involved, or maybe we could create regional zones for the trading in these mutual funds. And we could bring in money, and eventually when they are stable enough, maybe some retirement plans and things like that could be involved here, so that you're thinking and investing for your future by putting it in energy also. That's one area. The other area is, notice I didn't say 50-50 partnership between the government and the utility. I want companies to get directly involved in a partnership with the government because they can get tax benefits from doing this kind of work. And the government can put in some money, create this kind of partnership, and then award money based on merit and not the size of the candidate. This is very important. When money is small, a lot of the large institutions get it for very good reasons. They have better relations and they have better method of expressing themselves and responding to proposals because they've got big teams who can do that. I want that part to get away, and I want there to be a meritocracy that is based on how sound the idea is scientifically, rather than I'm with this company or that company. And I think that by having this type and having billions of dollars in these types of funds, you could start doing that kind of stuff. The next one is to build a private sector finance consortium. And this is kind of like technology innovation at EPRI. Okay? So we're talking about novel ideas that you may not see the result today or even 3 years from now, but 7 to 10 years from now you can. So if you want to have sustained creativity, you got to invest in those long-term type things. So that could be another type of financing mechanism. And then, of course, scholarships. I have seen Soda Hall at UC Berkeley for computer science. Now, I know that they're not selling beverages over there. Okay, it's the computer science department. And someone called Soda, last name, donated a lot of money, and the building is called Soda Hall. Just like we have Corey Hall and EE department. So if that is possible in other disciplines, I think it's possible in smart grid also. And we should encourage the Marvells and the Qualcomms and the Atmels and the Ciscos and others to establish these types of scholarships at universities, at colleges, at vocational training programs. This will not only help them hire the right kind of people when they graduate, but it creates the incentive for these students to remain plugged in, invested in this business. Because they're always making an economic decision. Should I go and work for Facebook, or should I do smart grid? Should I work for LinkedIn, or should I do smart grid? And these are real decisions. All right. So here are my concluding remarks, and I will really focus you on the last one. Smart grid, Uncle Sam needs you and your wallet. So what I mean by that is that we all have to participate in the financing of the next wave of smart grid. But what is missing are the financial instruments and the institutions that would give us enough confidence and reliability that when we put our dollar, hard-earned dollar that we've saved, that it will be put to good use. And I feel that we are lacking those institutions. We have VCs, we have Small Business Association of the government. I mean, we have these other things, but there's nothing focused that will nurture smart grid. And I feel that we're all collectively intelligent enough to start thinking about building such things. And with that, I would like to now open it up for a discussion and questions. Oh, okay. Patrick Duggan liked it. All right. So while you pose your questions on the chat, I'm going to start reading them. And if there are questions here in the room, I will take them also. So starting with Chris.
Yeah. When you were listing out some possible strategies, if you will, for alternative funding things, the one thing that seems to be gaining increasing popularity, especially with that younger crowd that you referenced earlier, is crowdsourcing.
Yeah.
Do you see that as a viable strategy, or is it just like wind and solar, too erratic to be dependable?
So give me an example of how that would manifest itself for smart grid, and then I can tell you.
I see that mostly in the category about supporting, helping novel ideas from grad students and that sort of thing. I don't see it as mainstream plant financing, but for someone to be able to say, hey, I've got this really neat idea about this, you know, go on the internet, I'll get 100 people to give me $100 each, and I can test this to see whether it's even viable, and then we can move it down the line if it is.
Right. So I think that the institutions that are involved, whether it be universities or colleges, need to appoint someone from their faculty or someone from their staff who would kind of be the ombudsman for that. You'd need some structure to it. So I would call it a semi-structured, where you allow the young ones to be innovative enough to solicit the money, but there has to be some institution that will collect that money and that will dispatch it and make sure that it's used properly.
Okay.
So I would say semi-structured.
Okay.
Yes. Other questions? Let me look at the ones in the room. So the first one is, I believe storage will be critical to soften the impact of EV chargers on the grid. The vehicles move. What utilities really need is better electrical permits that provide rating and load duration per charge for a vehicle charger and are communicated to the local utility, particularly when chargers are not yet ubiquitous. They will have high usage factors for family, friends, and maybe even eBay timeshare. Oh, all right. And then he says, so I don't know how to respond to that, but to say it sounds good.
Well, doesn't that sound a lot like the tiered pricing and DR capabilities that some of the utilities are putting into place, where if you charge your car during this time frame, it costs this much.
Yes.
But if you charge it 2 hours later, it costs that much less.
Yes.
And you kind of make the choice there, and your charging station does communicate your decision about when to charge back to the utility, who then applies the rates and can plan for the amount of current draw necessary to do the charging. Yeah,
I think that having sub-metering, having the ability to see what your electric vehicle is using versus the rest of your house, and then creating certain incentives at certain times when the utility feels they have excess capacity and encourage them to charge then, are all good ways. But I also believe that with the deeper penetration of electric vehicles, despite all of these economic incentives, there is an infrastructure issue that needs to be addressed. And that infrastructure issue is really bad at the edge. And if there was a proper business process which allowed the infrastructure improvements to be monetized through the purchases of these vehicles, like there was some kind of tax that the DMV or someone, you know, like the way we charge a gas tax. The problem with electric vehicles is, how will we charge a gas tax? Because we won't have a gas consumption to tax. So there has to be some equivalent of that needs to come as a surcharge, so that as the electric vehicles are being charged, that there's money available for those upgrades. Because I really worry that if it's coming out of the utility's bottom line, we're going to have problems with quality. So there has to be a mechanism to generate the money for it.
So how do you see, so say you had like an IBM or a large company come in and decide they're going to invest in the smart grid, how would you see that money being ideally used to move the smart grid forward? Like, would it, like for example, like in a PG&E or a CalISO, they run different parts of the grid. Would you see going to a smaller kind of micro area to focus on that first? What's your opinion on how that would be approached?
So I see companies like IBM or Accenture or SAIC or any integrator really as implementers. So the idea is that there are other people who want things done, and they come and help do it based on their expertise. So I don't see any issue with them participating in what I'm talking about. What I'm talking about is a grassroots movement that is needed to transfer some of the money that's sitting in treasuries of companies or in savings account of people into the economics of smart grid, so that not only the IBMs and SAICs and Accentures and others can survive, the big ones can survive, but there's enough money to go around for medium and even small people to participate. Now, I also believe that this will also give rise to small business set-asides that can be done. When you have enough money, you can do that. So then a company like IBM can come in and get the contract, but then they are told that 10% of it you need to give to small businesses. So then there'll be a secondary market in which they'll come. But if the money is limited, their first priority is to support themselves, their payroll. Why would they want to give some small business a chance? So this is all a result of how much money comes into the thing. And all I'm trying to do through my presentation is first create the argument for why it's needed, because there are still huge voids in R&D. This is not a done deal by any stretch of the imagination. And two, the argument that federal funds is not going to be enough to pull off the needs for the next 10 to 15 years, given sequestration, given what's coming out of the government. And I don't blame them. I mean, they can only do it based on the collections. And as the economy is slowed down, right, and there's a huge deficit, there's only so much money to go around. So I feel that this is the time when the private sector needs to develop these organizations and these financial instruments to bring little money, kind of like the way Ron Paul ran his campaign, where he collected $10, $50, $100, and it made a difference. I mean, he was able to compete in a national election.
How do you prevent the scenario in that, taking what you said there, my first thought was fine, we're going to go out there and we're going to get $50 from 1 million people, put it into the smart grid, and pardon my using this term, but I'll use them as the bad example. PG&E skims the profits off of what we just paid for and laughs all the way to the bank. So how do you make sure that the little people who put the money in are protected in a way that says that they are at least not scammed out of their money by one of the big operators?
Okay, so this is where the distributed energy resources and who will own them will make a difference. I believe that a lot of the infrastructure, today 85% of infrastructure of electric sector is owned by utilities. It's not going to be the case going forward. With distributed energy resources, there are going to be many independent power producers. I'm not suggesting that there'll be new wires running, replacing the ones here, but look at what happened to the regional Bell operating companies. There were so many long-distance providers that started using that wire, and quite effectively today. So today we can have any long-distance service we want off of our AT&T wire. And I think in the future we're heading in that direction, where the electrons that will be flowing through the wires of the distribution companies may be coming from many people. And so there will be a very large market in which there will be smaller players where these strategic investments can be done. I think that the Public Utility Commission's role will remain. I don't think that's going to change, and we need that for customer safety, reliability, on that, all that good stuff. But it never hurts to have a private sector financing mechanism to bring novel ideas wherever they're needed. So if PG&E wants it, they'll have to buy it.
You already have that going on in Texas, right? Where you can decide who your electric provider is. Yes,
and we're headed in that direction.
You used to be able to do that in California too a little bit, because you could choose a green electric company as an alternative to PG&E or whatever, but that died not out of technology issues but out of marketplace issues. It was too expensive for them to compete, and people just walked away from it, and then all of that pretty much went away. So it's been tried in a couple of places. The difference is that when California was trying that capability, they didn't have the deregulation infrastructure that Texas has had that forced PG&E and these other companies to compete on a more or less equal footing.
Yeah.
So
I wanted to share some statistics with you. When we look at 2011 and 2012 and 2013, we have gone from about a little over $5 billion in 2011 in the U.S. to slightly over $4 billion in 2012, and 2013 is even going to be lower. And China will cross United States in 2013 in smart grid investments. They were just slightly below the US in 2012, but in 2013 they're crossing. Europe is seeing an increase in smart grid investments, and so is Latin America. US is the only industrialized society that I know of that is seeing a decrease in smart grid investments. And the reason why that is occurring is because the ARRA money is running out. But that also says something else, that the private sector contribution has been so small that the federal money drop is affecting the overall. And I think this is tragic, given the fact that we go around the world telling everyone that capitalism is the way to go. Capitalism is not about the government sector funding a bunch of stuff. I thought that was associated with socialism. So somewhere I forgot my political philosophy, but we don't seem to practice what we preach. And I'm here, I've been in the US 34 years, and I came on this dream that, the private sector is how we'll flourish. And I have to tell you that the Apollo mission and what it did to electronics and what has happened in healthcare as a result of funding from NIH, we need to create something like that. And we don't have anything like that. Everyone has just gotten used to federal money, and when it runs out, it's like a Darwinian rule. Okay, the little ones have to go, the big ones will stay. And I think that is unfair, because it's not necessarily the case that all the big establishments have all the creative ideas. There's no such connection. Just because you're big doesn't mean you know the answer.
In fact, it's the opposite, right? I come from technology background, I'm doing it for the last 35 years. It's always that bigger guys buy from the smaller, more innovative companies to get the solution, but they can make better use of it, right?
Yeah.
They can scale it up, they can take it to better
they have the financial resources.
Yeah,
yes.
Financial as well as marketing, everything, market reach, penetration, and everything, right?
Market in the sense that they've always had a captive audience in the past.
Yes.
They had a guaranteed market.
Yes.
And that helps, right? Because all of this that we're talking about, right? You're crowdsourcing. It works well for coming out with a wristwatch or a pillowcase or whatever, right? Support. But
is that a solar pillowcase?
Maybe inflatable, right?
Yeah, right.
But neither the $4 or $5 billion he's talking about, which obviously it's a matching of the ARA fund, as you can see from the number. It's just bare matching of the ARA fund, right?
Yep.
And forget about the crowdsourcing. Even that doesn't move the needle at all, right? We're talking about like a $450 billion utility industry, and with a 1 terawatt or 1.2 terawatt capex of a $2 million a watt, like it's a $2 trillion industry we're talking about. We're talking about 4 billion, 5 billion, and the crowdsourcing of a few hundred thousand.
What crowdsourcing doesn't move technology or the grid.
Yeah.
What crowdsourcing does is move innovation.
Right.
Yes, but it's also the scaling, right? Innovation at what scale, right? It does
But
move.
everything starts at small scale. Everything starts with some guy sitting in his backyard around the pool with a suitable adult beverage saying, gosh, I wonder if you could do it this way.
Right.
Agreed.
It all starts that way.
Yeah.
Your company started that way. I know it did.
Yeah. Okay. One thing I want to caution people is that the term smart grid investment, when you hear about 400 billion and 500 billion, a lot of stuff is now being lumped into those estimates that previously when utilities invested in the grid, they didn't call it smart grid, they just called it investment to maintain their grid. Now because it has comms technology and cybersecurity, they lump it in with smart grid. So I'm not suggesting that we're going to run complete utilities with the money we're talking about raising. I am talking about raising money to do very specialized research and development in specific areas which will address the problems that we're facing in the direction we're headed with DER. I don't think there are enough people in our industry who understand from an energy balance perspective what distributed energy resources, when they become a large percentage of the energy mix, in other words, at the expense of centralized plants, do from an overall stability perspective. So what the centralized plants have been doing is they've been acting like a shock absorber. Now, if you take the shock absorber out and you just say, I'm going to go on springs, and I'm just not going to go over bumpy roads so my spring doesn't oscillate like this, well, good luck. It's not going to happen. So one of two things needs to happen. Either an innovative new source of energy needs to come out from some amazing innovative research over the next 5 to 10 years that can act as the new shock absorber that coal and nuclear, when they're retired, go away, they need one. Or some new control theory is going to be developed in a university, mostly in the nonlinear side, with the use of informatics that will do a better job than it is today. But short of these two, I don't know how we're going to get into the 30 and 40% range, because that storage that people are talking about is a very expensive hobby, not from a kilowatt perspective, but a kilowatt hour perspective. There's a difference. See, a lot of people think, oh, if it drops by 20 kilowatts, I got a battery that can give you, but for how long? And if you add up all the valleys of every time the sun goes down or the wind drops, especially in the U.S., Holland is different. Holland is always blowing. They know exactly. They've been
in Texas.
Yeah, 500 years those windmills have been going round and round. So when arguments of like Denmark is a microgrid. Denmark runs on wind, and when they don't have wind, they go to Scandinavia and they get the energy from the hydro, or they go to France and they get it from nuclear. And they still call themselves 47 or 50% renewable. I'm like, come on.
I would even say that the crowdsourcing model could work, but I think it's so different for, like, say an electrical engineer or a computer science guy, because you can go and you can be creative and you can innovate. You can go out there and you say, here's my idea, and people are going to invest in it. I mean, I know a couple of CEOs that go and look at these crowdsourcing sites and look for innovation and say, hey, okay, I'll pay you to create, I'll give you more to create this or whatever. But when it comes to electricity and the challenges that you're talking about here, you almost have to have a base knowledge that's greater than what you would have by getting just a degree, say, at a good college.
Absolutely true.
Yeah.
Agreed.
And then one other thing I will say, as because we are just past our 7:30 time, but what I wanted to talk about was SGIP as an example. The Smart Grid Interoperability Panel has just moved from the public sector to the private sector. It has its own chief now. They were selected. It has working groups. But if you look at where the membership funding is going, it's largely going to support a skeletal group, while everyone else is still volunteer. Not only volunteer, but they actually have to pay to be a member in order to participate going forward. Now, my suggestion is that maybe we need to create a working group within SGIP to address these issues that I'm talking about, building these financial institutes. So just as important as standards for interoperability are from a technology perspective, or cybersecurity controls, financing is also important. Because if we don't have that, and they have learned the hard way by asking for members. See how difficult it was even to get membership. I'm talking about $10,000, $15,000 out of a company's worth hundreds of millions, because the CFO of the company asks, what are we getting for it? And until we don't have the proper arguments for that, if I go and tell the CFO of any Fortune 1000 company that you're not going to have electricity for 6 or 10 hours a day in 5 years, trust me, they're going to start putting some serious money into it. But how do we do that? We can't do that unless we agree as a consensus. There are people who are so taken by renewable energy, they think it's the answer to everything. And they need to meet some of the physicists and the electrical engineers who know otherwise and come to a happy medium position. And then together we can go to these Fortune 1000 companies and say, please invest in R&D for your availability of product. Then the argument is different. But today, unfortunately, there's so much ideology that's coming out, especially in some of the more progressive states. It's hard to even make the counter argument. I can do it because I'm here on a forum and I'm doing an audio broadcast and they're not calling back. But up to now, the thoughts have been good. I just want to read 2 quick notes and then we'll wrap it up unless there's some more questions. Are there any more questions? Okay, Patrick says, your child splashing in a pool analogy is very good. How do we compensate for the loss of the grid inertia provided by large centralized generators, don't we need a mix? And that is exactly the case. We do need a mix, and if these centralized plants are going to go away, I highly recommend that we look at small modular nuclear reactors in the short run. And EPRI is, again, doing good work there. The Nuclear Energy Institute is looking at it. There are several good conferences going on this subject. I believe there's a company called NewScale that is a startup type company that is in this space. Pebble bed, you know, the kind that where you do away with the fuel rods and you encase every pellet with its own encasing, so you don't have the concept of a meltdown and things like that. And then make it passively safe so that the enthalpy or the heat that comes, the residual heat after loss of coolant and everything, is absorbed in the reactor itself, so there's no meltdown. And then make them small, like 250 megawatts as opposed to 1.4 gigawatts. You can still put them in a bunch of them under a shield and build as you go. But these are the ways we can get out and we can address Patrick's issue until some other source. I think by 2050 or beyond, some type of fusion will be here. And the reason is because the materials technology is improving to that point where I can see that happening in 30. It won't be, unfortunately, in my lifetime, or I'll be very old by then. But maybe someone after me will say, yes, you know, Irfan used to talk about fusion. It turned into confusion about 20 years ago. And ITER is there, and they just keep talking about the tokamak, and I have my issues with that design. I don't think fusion is going to be solved in a donut, okay? You may glaze a donut with coconut, you may get a Krispy Kreme donut, but fusion and donuts don't go well together. If you study plasma physics, you'll know what I'm talking about. But politically it sells, and for 20 years it has frozen the development of fusion because the donut is sitting there. Okay. One last thing from Pat. Pat was busy today. Funding. Have private companies bid on commercialization rights for R&D ideas that are developed? The bid reflects the money they will spend on development, and they need to submit a plan. If they choose to stop the plan, it can be reassigned. So I guess this is a suggestion that he's providing. Yeah, I like that. I think everyone needs a little skin in the game. That is the message that I want to leave you with. And we need to have organizations like SGIG with their brilliant people from all over, from the different verticals of the industry, come together. And we started that actually with Lynn, the Professor Geisling, or Geisling. In the first phase of the NEST project, we were talking about economics, and then the people left because there was no funding to support their work. I think we need to bring back the social sciences people, the humanities people, and the political science people to help us build the right mechanisms. I mean, I look at Facebook, I look at LinkedIn, I look at these social net, and I'm amazed by the billions of valuation that they've created. I'm still trying to figure out what exactly is it. And here we're talking about electricity and survival, and there's no money. So something is wrong in what we're doing. My job today was to make you think, start thinking, and engage in this dialogue. So with that, I thank you all for participating. And at this time, if there are no further questions, I don't know if there were any in the Q&A. Oh, we have some questions in Q&A. All right, so William Miller says, the U.S. is not investing in microgrids. The EU has decided to do this. They have committed to renewable energy. The U.S. has decided to continue to waste energy. Everyone else turns off the light. We keep the lights on. We don't turn the machines off. Yes, good point. And I did not bring up the microgrids specifically, but I believe that a big relief for distributed energy resources is microgrids. Because if you can create a set of adjacent microgrids that are dependent on renewable energy, there is a rule of adjacencies that will start working to help supply energy to each other when one is missing and the other one has it. But it requires a type of regulatory framework change that would allow trading to occur between microgrids. Today, most states don't allow that to happen. And I think so it's more of a policy issue than a technology issue. And if we have this microgrid and we have these adjacency concepts, What we can also do is help with VAR support, volt VAR support, to stabilize the grid, and we can also rely on it for added resiliency in the system. So when we absolutely need energy from somewhere, microgrids can deliver it to us, because we can send a message saying who's got it, and if the cloud cover is not on them, they can provide it. So microgrids are an amazing thing, but in the United States, given the current policy framework, the regulatory framework, unfortunately it has become an existentialist game between utilities and microgrids in many states. And I worry, because we're going to miss out on this opportunity, while others, you know, I mean, when I say miss out on the opportunity, I mean in terms of producing microgrids, that China and other countries, and Japan and others, will take a lead on microgrids, and we'll be buying Japanese microgrids in America, and our money will be going out. So I think that we need to seriously look at microgrids. Okay, nuclear is too costly and exposure may be too high. Look at the Fukushima disaster. There'll be other equipment will age and there'll be failures. I agree, William Miller. The way we're doing nuclear today needs to change. And so as the current nuclear power plants are retired, just like we will not use 286 processors in our data centers today, why are we using boiling water reactors? To me, boiling water reactors are like 286 processors. Yes, they can do the job, but at a huge cost. So we need to be on cutting edge in all technologies, not just in solar and wind. There needs to be more emphasis on energy storage and recovery of energy and reduce wasted energy. I agree, as the former Secretary Chu said, the energy efficiency is such a low-hanging fruit, it's on the ground. But I have also great hopes in our new Energy Secretary, Moniz, who used to be, by the way, on the EPRI Industry Advisory Board at one time. Professor at MIT, has now been asked by Obama to become Energy Secretary, and I have very high hopes from him. A brilliant man. Okay, William Miller says, today's approach is too costly, too complex, and costs consumers too much. This is not good in a down economy. Agree. Pramod says, how is your idea number 3 on financing option different than what ARPA is doing? Okay. So if you look at the ARPA, as I understand it, it's working with individual companies, but they provide some seed funding, like they will award, as I understood it, and then the intellectual property belongs to that company and they take off. But I didn't see it as a 50-50 kind of partnership, the ARPA funding.
I have no idea.
Yeah. Because I've seen how ARPA money is spent. It's competitive, and there are certain applicants who get it, and it's like angel investment. But it's not a 50-50 partnership kind of thing. Okay, and then the next question is, Irfan, I think the government should find where all the billions went that were spent by the companies who were awarded money and not ask people for more money. Okay. Well, we have a very good idea of where the money went. There's great transparency in the SGIG grants because the reports are there on the website, you can see. The challenge is that a lot of money was spent on smart meters. So it hasn't had, as Chris was saying earlier, the fruition of all the applications that could be enabled by it, because there are certain impediments in home area networks, some technological and some to do with data privacy. So we haven't seen the full benefit of it. So it's not the case that the money was spent and we don't know where it went. But I think a lot of it was spent and there were some political implications in it. It wasn't necessarily for the best technical benefit. And I think in the future that will not be the case because people learn. Uncle Sam has no money, sequestration, that is true. But I think that as part of the agreement that Obama is trying to do with the Republicans, in which he's saying, okay, we'll be more fiscally responsible if you let us spend $50 billion more in research and development and other things. I think some of the money can come from that if a bargain is made. Cybersecurity is complex, it is broken. NIST is requesting a new cybersecurity framework under executive order of the President. The existing approach is broken, is inadequate. Web 2.0 technologies are highly vulnerable. We need to transition to Web 3.0. Okay, Web 3.0 is a semantic web that can provide metadata isolation and intrusion protection for physical protection. Cybersecurity cannot be addressed by policy alone, which is more or less what is happening. Okay. I believe that if there is adequate funding in research and development, there will be enough people involved, enough intelligent people involved, and then they don't have to go and make a living somewhere else. They can do it here. When you get their attention, you will get their opinions also. We can build consensus on those opinions and move forward. The reason why we have people like William Miller saying these things in isolation is because he has taught these things, but there isn't adequate funding to carry his thoughts to fruition. I know him personally. I know how many organizations he goes to. We need more critical thinking. Yes. So we know how many places he goes to on his own dime. And he's promoting things that are going to help in machine-to-machine interaction, for instance, which is going to be big going forward. But the standards that he's promoting are falling largely on deaf ears in the US. In Europe and elsewhere, amazing. Because everyone is thinking about expediency when you have little money. It's like, how do I survive? How do I maintain my job or my company's position in the market? But when there's enough money, when there's prosperity in the process and there's recurring money, then people become more generous. As you remember, the United States in the 50s and 60s was a different country than it is today. So with that, take back to the 50s and 60s. I was thinking of a TV program, but the one didn't come to mind. Leave It to Beaver, was it?
There was a program in the 50s called Leave It to Beaver.
Yes. Okay. And what was the one with the policeman and that?
54, where are you?
No, the one where they were in North Carolina somewhere with Andy Griffith. Oh, the Andy Griffith Show, yes. So with that take back, I think Sweden is now adopting XMPP for the, see, I said Europe and he said Sweden. Okay, very good. So with that, I will conclude and thank you again for participating in an engaging dialogue. And I hope this will stimulate you all to start thinking about how we can create the proper financing mechanisms for the next wave of smart grid investments. Thank you all and have a wonderful evening.
For the couple of people that came